The discrete math students. Got another example of induction for you. You know, if n examples of induction proofs is good, n plus 1 is better. So let's do another one. Let's prove an inequality by induction this time. Now, inequalities, you got actually an extra measure of freedom there because you don't have to preserve things exactly like you do when you're proving inequality. So you can kind of throw stuff away. Sometimes you got some more wiggle room, but that can actually make it even a little harder to see what to do because, well, you know, what should I throw away here? You don't want to throw away too much or you end up not being able to get to your goal. So there's a delicate balancing act. That said, I don't think this one is too complicated. Let's take a look. Okay, we're going to prove that for every positive integer n, 1 over n factorial is less than or equal to 1 over 2 to the n minus 1. Okay, so again, we can do analysis to our heart's content here, but let's just see what happens. Let's launch into the proof. So we'll say proof, and as always with our advanced proof methods, we want to say what method we're using. So I'll say we'll give a proof by induction. Okay, once again, we're looking at z plus as our domain here, which means that our base case is n equals 1. So we'll say for n equals 1, 1 over n factorial. So we're looking at the left side here is equal to 1 over 1 factorial. 1 factorial is just 1, so we get 1. Okay, and then we go take a look at the other side. 1 over 2 to the n minus 1. Well, that'd be 1 over 2 to the 1 minus 1, which is 1 over 2 to the 0, and we can see that's going to be 1 as well. So what we actually got here was equality, and that's fine because this is not a strict inequality. It allows equality, so we're fine here. So since 1 over n factorial equals 1 over 2 to the n minus 1, we can also say that 1 over n factorial is less than or equal to 1 over 2 to the n minus 1 when n equals 1. And there we go. Our anchor step is complete. Launching into the induction step now. Again, there may be some analysis to do here, but let's just go ahead and get it started. We'll put a new paragraph here, and we'll say, now let k, we need an arbitrary element of our domain here, which again is z plus for this problem. And this would probably work for n equals 0 too. We could have used a different domain, but oh well. And now we're going to assume that the inequality holds for k. So we'll assume 1 over k factorial is less than or equal to 1 over 2 to the k minus 1. Okay, well, we do need to think about what's going to happen for k plus 1 now. Let's see if we can fit some analysis in over here. Okay, so we know what our goal is. We want to have k plus 1 in there, so we want to do 1 over k plus 1 factorial less than or equal to 1 over 2 to the k plus 1 minus 1, which, you know, we see we can write that a little more nicely already, 1 over 2 to the k. And let's see, how are we going to get that? Well, again, we got to find some way of relating this to our induction hypothesis, which, as you can see, we just put in our proof over there. And one way to get that involved is we could take a look at that. So k plus 1 factorial. Okay, this is the product of all positive integers up to and including k plus 1. So all positive integers less than or equal to k plus 1. Well, another way we could write that is k plus 1 times k factorial. Because k factorial is a product of all the positive integers up to and including k. And if we multiply by k plus 1, now we got the product of all positive integers less than or equal to k plus 1 again, which is what k plus 1 factorial is. So we could leverage this now and say, well, if I look at my left-hand side, 1 over k plus 1 factorial, that is equal to 1 over k plus 1 times k factorial, which in fact is what we just took a look at. And that's pretty cool because I now see in here, maybe I can make it even a little clearer, 1 over k plus 1 times 1 over k factorial. That's now the left-hand side of my induction hypothesis. So if I use my induction hypothesis here, I can say this is less than or equal to 1 over k plus 1 times 1 over 2 to the k minus 1. Okay, so we are starting to get there, and if I look at my right-hand sides as well here, well, 1 over 2 to the k, I could also write that as 1 over 2 times 1 over 2 to the k minus 1, and yeah, that's not quite going to fit. Anyway, this is looking really good. So all I need at this point to get everything to go through is just 1 over k plus 1 is less than 1/2, or less than or equal to even. And that's going to be true because I've got k being a positive integer. I know k is greater than or equal to 1. So k plus 1 is greater than or equal to 2. And then if those are my denominators, so 1/2 has the smaller denominator. And with a smaller denominator, it's going to be a bigger fraction, or greater than or equal to. And voila, we now have our plan for how to execute the induction step here. Yeah, it was a little bit messy, but that's the nature of analysis sometimes. We got to take it now and clean it up for our proof. Okay, so there is a lot going on here. Rather than trying to do that all in one stream, maybe let's say a little bit about this before we launch into that k plus 1 case. So let's do that last part that we just did. Let's put that first, which again is not surprising. Often happens when we go from analysis to the proof, we're kind of reversing the order of things. So I'm going to say since k is in z plus, k is greater than or equal to 1. We know that 1 is the smallest positive integer. And so k plus 1 is greater than or equal to 2. Let's take this one more step. Again, you can kind of switch whenever you feel like it here to looking at the k plus 1 case. I'm going to say, thus, 1 over k plus 1 is less than or equal to 1/2. Okay, that's kind of the key point here, as we saw at the end of our analysis. Now let's look at the k plus 1 case. See what happens. So for k plus 1, we have the following. So we look at our inequality. It's going to be 1 over k plus 1 factorial. Okay, so that's our left side. Now we know that we want to get to the right side, which we could think in any of these ways. Basically, we want to get to 1 over 2 to the k, and we can do that using inequalities as well as equalities. Let's start with an equality, and as we mentioned, we'll say this is 1 over k plus 1 times k factorial, and then just to make this even a little clearer, let's put it as 1 over k plus 1 times 1 over k factorial. We know we can rewrite fractions that way. And as we just saw, 1 over k plus 1 is less than or equal to a half. So let's put that in. Make that substitution. Here's where we get our inequality kicking in. Okay, so now we got 1/2 times 1 over k factorial. And now that we got that k factorial nicely in there, we can use our induction hypothesis. So let's say this is less than or equal to 1/2 times 1 over 2 to the k minus 1. Okay, here's where we used our induction hypothesis. Okay, I guess that came out all right. Okay. And now I think it's debatable. Do we want to put in a step here where we just say 1 over 2 to the k? It's probably all right to do that. I don't think it's necessary by any means, but we'll say 1 over 2 to the k when we multiply those fractions together. But really here, the way we want to write this, which we could have gone to this right away, is 1 over 2 to the k plus 1 minus 1. Okay, now we can see, yes, indeed, this is the right-hand side of my goal. Just with k plus 1, well, it's k plus 1 substituted for n. We started with the left-hand side with k plus 1 substituted for n. All our inequalities, where we have them, are going in the right direction. And that completes our induction step. We've reached the goal of the induction step. And so we can say, let's say, thus the inequality holds for k plus 1. Okay, we could leave it there. We could put a wrapping, another concluding sentence. Let's do another concluding sentence this time. I'll say therefore 1 over n factorial is less than or equal to 1 over 2 to the n minus 1 for all n in z plus by induction. And now we'll say we're done. We got a nice wrap up there. Really kind of forcefully state that conclusion. We've proved what we were trying to prove. And so that's it. Again, I hope you see that although the details vary and look a little different depending on what statement you're trying to prove, there is a fair amount of consistency in the structure of induction proofs. So leverage that and get really used to that, how they look, be familiar with it, so that you can then kind of focus on getting those details, the algebra, to work out in each individual situation. I think that's really important to have some of those things down, kind of like knowing where the gas and the brake are in your car when you're driving, so that you can focus on the traffic situation that you're in. All right, so that's another example of an induction proof, maybe the last one for now, but who knows? We'll see you next time.